University, and he got there his PhD with under the supervision of Martin Plenio, and now he's a professor in China. His research focused on quantum optics and in particular quantum sensing and metrology, and more recently the study of frustration in quantum optical scenarios. And about this topic today, he will speak to us about frustrated superradiant phase transition. So please, the stage is yours.
Okay, thank you, Nico, for invitation. So it is my great pleasure to talk about this work on frustrated superradiant phase transition with you. The goal of today's talk is just to introduce this notion that we have been studying for the past couple of years. So the idea is we have this phase transition that is very well known in quantum optics. It's a ground state superradiance, and we will see how we can impose the notion of the frustrations and what would be the result and the physics of it. So just to be on the same page, like maybe, I mean, we don't really need a cavity QED introduction here, but just in case, cavity QED is a study of interaction between the quantized light and the matter, and there is many different realizations of this cavity QED physics with a very long history in quantum optics. And one of the most basic description of the cavity QED system is called decay model, where you can describe this electromagnetic wave inside of the cavity as a single harmonic oscillator. And then if you have many quantum emitters, each of them two-level systems, then you can consider that as a collective spins. So that this decay Hamiltonian is a single mode harmonic oscillator with large angular momentum and dipole interactions between them. And if you look at this Hamiltonian, there is a nice symmetry, which is a parity symmetry. Basically, the number of excitation is not conserved because of these counter-rotating terms that we have in the interaction term, but still it's parity, whether it's an even number of excitations or odd number of excitations, they are conserved. So what that means is if you find the ground state or any other eigenstate, it should have a very well-defined parity. But there is phase transitions when you crank up the interaction strength lambda, where this parity symmetry is spontaneously broken. So if you look at the ground state expectation value of A, if eigenstate preserves the parity, that has to be zero by symmetry. And it is true when lambda is below certain threshold value, and we will call this a normal phase or symmetric phase. However, above this threshold, a spontaneous symmetry breaking of this parity symmetry occurs. And what that means is this cavity field creates a spontaneous coherence. And in terms of atoms, the collective atoms, that means spins builds a spontaneous polarization. So then, because of this parity has two choices, even and odd, when you break them, then you will have two degenerate ground states. So this is a superradiant phase transitions that is well known to occur in the decay model in its ground state. And there has been some experimental observations. The example that I show is a little bit different from the one that I showed you before, because this is now involving a cavity loss, so that we are now talking about the steady state phase transition, but not the ground state one. But the phenomenology and the symmetry breaking is more or less same. Here you have a BEC trapped in the optical cavity, and if you have a strong transverse laser applied to this BEC, then this process of photon scattering from the transverse laser to the optical laser and the interaction of the BEC motional modes, they are described effectively by the decay model. And when you crank up this laser intensity, then there is this superradiant phase transitions where spontaneous polarization of the cavity of these spins and spontaneous coherence of the cavity builds. This has been well observed. And interestingly, in this case, collective spin actually correspond to self-organized momentum states. So this is a little bit of details, but this superradiant phase transition in non-equilibrium settings has already been observed, and there are many exciting experiments around. So then the decay model is realizing the traditional thermodynamic limit by having infinite number of atoms. But about 10 years ago, with Martin Plenius group, in the Martin Plenius group, we made another prediction that you can actually have a finite number of atoms, where then it is not in the thermodynamic limit in the traditional sense, but you can still have this infinite ratio limit where the ratio of the atomic frequency to the cavity frequency diverges. Also, the coupling strength compared to the cavity frequency diverges as well. But then you have this control parameter G, which controls these two relative infinities, finite. Then you can have a very well-defined control parameter G. And in this limit, we have shown that the Rabi model or decay model with only single atoms also exhibits the superradiant phase transition with the same critical properties. You see here ground state superradiance, and just like any other quantum phase transition, the spectral gap closes at the critical point and number of photon diverges. I haven't shown it here, but the squeezing also diverges as well. So this is a one atom version of superradiant phase transition. It is also often called finite component system phase transitions, to emphasize the fact that there is only a finite number of components, but the thermodynamic limit is realized in terms of parameters. And there was also some attempts to observe this in experiments.
Myung-Joong, can I ask you a question regarding this previous slide?
Yeah.
No, previous slide, please. Ah, yes, this one.
Yeah.
No. The one after.
Here.
Next one.
This one?
Yes.
There is some delay, but it's okay.
Okay. So you're saying that this model is for a single atom, right?
Right.
So I was wondering then, what is the meaning of JN operator? And
so this is just a spin half, right? So the angular momentum is 1/2.
But then, why you have this n index in the J operator? You have only one atom, right?
Oh, right. So this index is like I'm going to use it when I have many modes. But at the moment, this index is meaningless. It's just a local index.
Okay. And last question.
Yeah.
And what about NA? How should I understand NA?
Oh, NA at the moment is in this example will be 1. So in the standard decay model, this will be large, but in this case, NA can be said to be 1.
So this is just the Rabi model for a single atom. Yeah.
Right. Exactly.
May I ask a question also on this single atom phase transition? So in this case, basically, right, you are taking this eta parameter going to infinity. So can you work in the dispersive regime? So like could you gain some understanding of this system if you, made the usual expansion up to second order that one does in dispersive regime? Is it how you derive this phase sensation?
Yes, so basically then spin up will be highly energetic. So you can integrate out the spin up using Schrödinger-Wolff transformation. And then you can find the effective and exact effective Hamiltonian. In the decay model, that will be having two bosonic modes coming, one from the cavity, the other from the collective spins. But in this case, it will be only the cavity modes Hamiltonian that will describe this closing energy gap, for example, in the center below, and the diverging fluctuation on the right-hand side.
So basically, in this case, doing so, you are losing all the information about the atomic state, right? Because you are basically sending it to infinity and tracing it out.
Right, precisely.
Okay, thank you.
Yeah, thank you. Yeah, so then with single atom, there are many candidates where you have a very nice control and possibility to engineer these rather peculiar parameter regimes. Although this ratio won't be infinite, but we want it as large as possible. And then this will play the role of finite size effect. And this some evidences of this transition has been observed. And the reason why I'm showing this is this illustrates this Superradiant phase transition with a single mode can have many different experimental platforms to be explored. In the standard decay model, you can have many atoms or a BEC, as I showed it before, or in the single atom limit with the Rabi Hamiltonian, you can have trapped ions or the superconducting qubits where you have more controllability. And now I would like to introduce frustrated Superradiant phase transitions. And this work was done with my former students at Jinchen Zhao, and some of the work in preparations with Zhongjun Li. And just brief like refresher on what a frustration is, right? I mean, the most well-known example is if you have a spin half particles on a triangle motif, and if you have Ising interactions but anti-ferromagnetic interactions, so that spin on the vertices want to be anti-aligned. And if you two of the spins decided to anti-align and the third spin doesn't know what to do, and this is the source of geometric frustrations. And in this triangle motif case, you have 6 degenerate solutions, all of them equally unfavorable or equally favorable, depending on how you want to look at it. And while this is a interesting extended degeneracy, I mean, this, if you now extend it into the 2-dimensional lattices where with this triangle motif, then you can have many interesting phases coming up from this geometric frustration. And this is a active field of research. And where in cavity QED physics, in quantum optics, there has been also very interesting research directions where if you have these many atoms inside of the cavity, this cavity field can mediate interactions among the spins. And if you mediate the interaction in a way that it induces geometric frustration among the spins, then you could realize spin glass physics or spin liquid physics. And this has been explored actively in a cavity QED setting. I think this is an exciting field because we not only we have great controllability to design these interesting many-body spin systems, these are also inherent in non-equilibrium systems so that many interesting physics can be explored. However, the question I want to ask in this talk is the opposite, right? Now, if you have a 3 interacting bosons instead of three interacting spins, is there any way to induce frustration among these bosoning modes, right? So let's think about these three resonator. So here I just took out a superconducting microwave resonator, and if you have capacitive coupling between them, then you can have these simple photon hopping interactions. And you can change the sign of these interactions by engineering the phase of this mode profile. But suppose you have done that, but if you ask yourself what is the result of this, if there is any frustration or not, well, the answer is no. We all know this is simply three harmonic oscillator, and when three harmonic oscillator interact with each other, it just forms a normal mode. And the sign of this J, photon hopping energy, it just changes the relative energy of the dispersion, meaning when J is negative, zero momentum mode, the spatially homogeneous mode will be the lower frequencies, and if J is positive, the other way around. So it's boring, right? So then, unlike the spins where there is a strong nonlinearity, for bosoning modes, we will not expect any frustrations. However, I showed you that if these local boson modes have an interaction with the local spins, and if this spin is made to be very large, then there can be a Superradiant phase transitions. And in this Superradiant phase, not only you have a non-zero cavity coherence, there is a sign choice because of the G2 symmetry. So you can have a positive sign for the cavity coherence or the negative sign, or you can consider this as having a positive displacement for the oscillator or the negative displacement for the oscillator. And for this, in this Superradiant phase, then, if you think about the mean field energy of these photon hopping interactions, well, then this becomes a multiplication of a coherence in each site. Site I pick up the coherence alpha I, and site I plus 1 pick up the another coherence at the local sites. And then this J has a very different role. So if J is negative, then when each local cavity pick up this sign, they will try to pick up the same sign, because then they can lower this hopping energy. So in this case, I drew a 3 double well potential, right? So each double well represents a single cavity. And while there is a sign choices, when J is negative, they must choose the same sign among these 3 oscillators. So there will be 2 choices. Then it will be same as the single side superradiance. However, if J is positive, now the neighboring sides should choose the opposite sign for this cavity coherence. And then if 2 of the cavities pick up the opposite sign, then the third one doesn't know what to do. So this sign choices, it is exactly same with the frustrations that antiferromagnetic Ising spin experiences. So this gives us intuition that if we allow a local spin interactions with the bosoning modes, and if we make that interaction very strong so that Superradiant phase transition is induced, then there could be frustrations among these sign choices of the Superradians. So with this intuition, let's build up a simple model to study this. So you can have a decay lattice model on a 1D chain. So each lattice site will realize 1 boson mode coupled to 1 collective spins. This can be a Rabi model as well, right? You can have just one bosonic modes coupled to a two-level system, but then you have to take this infinite frequency regime. But let's focus on the decay case. And you can also have these hopping interactions that we just have introduced between the neighboring sites. And then if you look at the mean field energy, and you can integrate out the atomic degrees of freedom first, and this is the effective mean field energy with cavity feed only. And then the local site has this alpha square minus square root of this 1 plus 4g alpha square. And this is basically single well to double well transition. When G is smaller than 1, alpha 0 will be the minimum. If G is larger than 1, then you have this double well transition, so you can have two different solutions locally. But this blue box is the hopping energy, and this is the force to that make choices about a neighboring cavity field. So then by minimizing this, you can find the ground state solutions. And just as we expected, when J is negative, all of the local cavities pick up the same sign, and then this superradiance looks exactly same as the single site decay superradiant phase transition. So this is a homogeneous superradiant phase transitions. And now if you look at the J positive case, the solutions, this is one of the 6 possible solutions you can get, right? So this is site 1 with the black square pick up the negative sign, while the site 2 and 3 pick up the positive sign, right? So there will be 5 more different sign choices like this. And so this increase the degeneracy of the ground state is the result of the geometric frustrations. And also what's interesting is for the Ising spin, when you have this 6 degeneracy, their angular momentum is fixed with the 1/2, so this magnitude is not changing. But here, the value that is experiencing the frustration is alpha, which not only has a sign, but also magnitude. And you can see that the system can minimize the energy by having a larger amplitude for the sign that is different from the other two. Okay, so this amplitude modulation is a feature that is absent in the spin case, and we will see that this will play an important role. So this is the what we call frustrated superradiant phase transitions. In the mean field level, if you look at the superradiant solutions with the positive hopping energy, you have not only spontaneous broken parity symmetry, but you also have this spontaneous broken translational symmetry, okay, as a result of a frustration. And then that was the mean fields. Then we can also look at what is the fluctuations around this mean field solution at the Gaussian level. So first, when J is negative, right, you can expand the quantum fluctuations around a Gaussian fluctuation around the mean field solutions. Then you have a Gaussian Hamiltonians, and you diagonalize it, then you can get this energy spectrum. And it shows a very common feature of the decay superradiant phase transition, where you have a closing gap and its exponent is 1/2, because this is a model where mean field becomes exact. So this is very typical. But for J positive, on the symmetric phase, when G is small, smaller than the critical point, you have this same mean field behavior. However, in the broken symmetry phase, there is something interesting happening. So what we have here is we have 2 different momentum modes closing each gap at the same time. and they have different power law exponents. So we see one mode which closes gap with the same mean field exponent 1/2, but there is this additional modes that closes this gap with a exponent 1. This is a feature that is missing in the other mean field time phase transition. And in fact, having these two different time scales, so this closing energy gap, inverse of it determines the time scale which diverges, and this is the famous critical slowing down. But there is two distinguished time scale that governs this critical slowing down, and there are not so many known examples that exhibit such a kind of behavior. And because this additional mode with the exponent 1, that is only appearing when we have a frustrated SPT. So we are going to call this a frustrated mode with exponent 1. Okay. And we can also look at the ground state expectation values. For example, we can look at the photon number of a local bosoning mode, and where this is supposed to diverge in the at the critical point with the mean field exponent 1/2 for the decay model, and this is same for the J negative. But for J positive, what you see here is one cavity will diverges with mean field exponent 1/2, but the other two cavity will diverge with the exponent 1. So there is a different critical exponents governing different sides of the cavity. Okay, so this can be used as an experimental proof of this frustrated SPT, because it's common that you can have this local access to the photon number measurement. But this is also a very exotic feature of the frustrated Superradiant phase transitions. This locally dependent critical exponent for the photon number. And now you can also increase this number of sites from 3, right? So here are a few examples. You know, when number of atoms is 7, for example, you will have frustrated solutions with extended degeneracy. But if site is 8, in fact, for any even number, then you can have perfect choices with just positive and positive negative configuration. This is comparable with the number of lattices. So you can clearly see that for any odd number of sites, there is this frustrated Superradiant phase transitions. And if you look at the energy excitation energy of this lattice model, for 7 and 9, you see that this frustrated mode, whose exponent was 1 for 3 lattice case, has now even larger critical exponents, like N7 and 9. And if we do these numerics, then we find that this exponent actually increases with N. So then this tells us that if we keep increase this number of lattice sites, well then in the infinite limit of N, so when we have a macroscopic lattice with an infinite number of sites, maybe this frustrated mode becomes massless, then we will have situations where if N is odd, we will have a massless excitation or a very, very light excitations. But if and a number of sites is even, you may have no such a merciless excitation. So the even-odd parity seems to have a big impact on the nature of not only the ground state mean field solutions, but also the nature of excitations. Okay, so then to make sense of
Sorry,
this,
can I ask a question?
Sure.
So do you expect this even odd difference to hold also in the thermodynamic limit? I didn't understand this point.
Yes,
that's right.
Yes.
If you
Yeah.
go to the limit of n equal to infinity, right? In principle, you cannot distinguish between even and odd number
Right.
of sites.
So exactly, that's a very good point, and this is something that I want to explain now. So this was the same question we had, right? It will be odd if this even odd parity changes the bulk property, right?
Okay.
But what is actually happening is if you have even number of sites, then if in the symmetric phase, if you look at what mode is becoming critical, and that mode is simply having a pi, it's a pi mode, meaning that if this pi mode becomes critical and goes into the Superradiant phase, then you have a staggered order parameter whose period is basically 2, right? So it's just you repeat the up and down configurations for neighboring sites, so that will be n odd even. But if you have odd number of sites in the symmetric phase, if you look at what mode actually undergoes it becomes critical. So this n minus over n pi mode becomes critical, and that actually determines the order parameter configurations of Superradiant phase. And this pattern that I showed you in the below is the order parameter configurations for any odd number of sites. And the key insight here is that this odd parity have an impact not only at a local site. This is not a domain or limited at a local site 1 or 2, but it has a global modulation of the order parameter. So it has this domain war, so to say, but this domain war size is now on the order of system size. So because this even and odd parity changes the order parameter configurations in a scale of the in the order of magnitude of a lattice site, so it is not surprising that this will actually give a different excitations, a spectrum for n and even. So here the key is these even and odd parities will not create a domain where there is a order of 1, whose effect will vanish in the thermodynamic limit, but it will create a domain where which is order of n, so that it will actually have a visible effect, which was this additional massless excitation. Okay, then how can we relate this to this extreme softening of the additional frustrated mode? This is basically, there is some emergent continuous symmetry, right? So when we have this large domain war, when we shift the every site by 2, there's still this configuration will have same configuration. So there is this additional translational symmetry is appearing. And I think this schematic figure on the bottom is the easiest to understand. So as we increase the number of n, the number of degenerate solutions are increasing with n as well. Because of the frustrations, there are there are many degenerate ground state solutions, and all of them get softens and softens. And as you increase the n, these different energy minima is now smoothly connected, and it does not take much energy to go from one energy minima to the other, and that is the source of this massless excitation. So we can understand this as a Goldstone mode, but this is an emergent one, right? I want to emphasize that our underlying model, the decay model, only has D2 symmetry, not a continuous symmetry, but this emergent continuous symmetry is arising because of these geometrical frustrations that we have in the decay lattice. Okay, so then we had fun with frustrated Superradiant phase transitions. I think we now understand fairly well what is happening in the 1D lattices, but even in the 1D lattices, we can now have some phases when photon hops from the one mode to the other in quantum optical systems. It is now very feasible to engineer some phase. This is also called the Pierce phase, and this corresponds to adding a flux, threading a certain loop made by these resonators. And what it does is it plays the role of a synthetic magnetic field, and it breaks the time universal symmetry. And the natural question we can ask is, what is the nature of the frustrations in the system where time universal symmetry is broken? Okay, so that will be my next topic. So I will not go into too much details, but now here is the phase diagram. So on the x-axis, I have a phase, right? So I will tune this effective flux or effective synthetic magnetic field strength on the x-axis, and on the y-axis, this is the local light matter interaction that controls these Superradiant phase transitions. Okay, so when theta is 0, this corresponds to J positive case. So we should have from normal phase to the frustrated frustrated Superradiant phase transitions. And when this theta is 1, J is negative, so we have this homogeneous phase transitions. So when you tune this theta, this frustrated Superradiant phase is robust. So there will be an area where this frustrated phases arises. And on the right-hand side, you also have a stable Superradiant phase over certain ranges of theta. And then they meet at a certain critical value of flux. So this at the critical flux, first order transitions between these frustrated Superradiants and the homogeneous Superradiants occurs. Then this one point at the middle is the tri-critical point. Okay, so that's the broken symmetry phase. And that is not so surprising because we have on the left limits of frustration, on the right limit, you don't have frustration. So when you control a complex phase, there is first order phase transition between them. But what is also interesting is the behavior in the normal phase. So on the right-hand side, NP stands for the normal phase. Right? This is the regular normal phase. But on the left-hand side, we have AMP, and this is short for anomalous normal phase. And this is where this normal phase shows some strange behaviors that are not found in the time reversal symmetric case. And that is these critical exponents. So now I am going through this one of the theta value on the left side of the critical flux. So it will go from the anomalous normal phase to the frustrated phase. And now if you look at the energy spectrum, on the left-hand side, the energy gap closes with the exponent 1. So this is different from the normal phase exponents 1/2 that we typically expect from the mean field time phase transitions. And on the right-hand side, the critical exponent is 3/2. Okay, so this is strange in a multiple perspective. First, in the normal phase, although there is no symmetry breaking, right, the way it closes gap is different from the time universal symmetric case. The more striking thing is on both sides of the transitions, the critical exponents are different. Okay, so if you recall your statistical physics class or textbook you have read, typically you assign a different critical exponents for both sides of the phases, but eventually you make it equal and you always have same values for both sides of the transitions. And this is basically the renormalization, the nature of the fixed point, right? It will have same eigenvalues, so it is governed by the single exponents. That is a typical explanations. But you have this quite strange behaviors where both sides of the transitions have different exponents. Not only that, if you look at the photon number, right, on the left-hand side, you should have a photon number that is diverging. That is what is typically happening at the critical points, right? You have diverging fluctuations. However, photon number on the left-hand side in the anomalous normal phase, the photon numbers are bounded. It does not diverge. On the Superradiant phase side, it does diverge. So this finite fluctuations in the normal phase is another anomalous feature of this anomalous normal phase in the broken time universal symmetry case.
Sorry, can I ask a question?
Sure.
So this result is derived still in the mean field, right?
So this is Gaussian fluctuation around the mean field.
Okay.
So this is a quantum calculation.
And do you have an explanation of this effect, or could it just be that the mean field is not the right technique to describe this system? I don't know.
Oh, we still expect the mean field to be exact, right? For this type of systems, there are works from Hep and Liv in the old literatures, and there are also recent very nice work from the Igor Rezanovsky's groups, where you can show, you can prove that mean field is actually exact. Right? And our model, all of the models that I'm considering here belongs to that class of the models. So I think the mean field is still exact, but the fluctuations around the mean field has this peculiar property. So I don't think this indicates the failure of the mean field, but this is this anomalous properties due to time universal symmetry breaking and also frustration.
Okay, thank you.
But indeed, I mean, it is curious why that's the case, right? Why there is this bounded fluctuations. In fact, that turned out to be rather has a rather simple origin. So if I look at the excitation, so dispersions relations as a function of k, I didn't even attempt to write the full expression because that is very, very dirty, but it has this structure. There is one term with a square root term, and then there is this additional additive factor. So when there is no time universal symmetry breaking, delta K is 0. And when you hit the critical point, this square root AK, the thing that is inside the square root becomes negative, so that becomes the unstable mode and so on. This is the very typical scenario, right? The way you have this critical point is having this square root singularity. However, if there is a time universal symmetry breaking, then the dispersion of a positive K and the negative K will have a difference. And this difference is controlled by a critical flux. Okay? And for below the critical flux, where this anomalous normal phase occurs, this epsilon K becomes is crossing 0 at the critical point. So although the fluctuation is not diverging and there is no singular this square root singularity that is common in this decay model or any fully connected systems will have this square root singularity. But by having a time universal symmetry and this asymmetric dispersion relations, this epsilon K accidentally crosses 0 and becomes negative. And when it becomes negative, the system becomes unstable and it goes into the broken symmetry phase. And that's the origin of these bounded fluctuations. So if you look at the fluctuations expressions, you see that there is this 1 over square root term, and that is typically responsible for the divergence of the photon number. But in the case of the time universal symmetry, before this square root term becomes 0, so that you have a divergent photon number, the normal phase is no longer stable and becomes unstable, right? So then this is the origin of this bounded fluctuation. Okay, so this is really a result of the time universal symmetry breaking and asymmetric dispersion relations. Okay, and I just want to advertise this relatively unknown work. I mean, maybe it was new to me. Many of you already know, but I mean, there was this paper by a statistical physicist saying critical exponents can be different on the two sides of the transitions. So this paper illustrates that for most of the models that we are dealing with in the statistical physics have a same exponents on both sides of the transitions, but this is not by any means restriction, right? We happen to have those models, but you can cook up models where these exponents are different. And what we have just found here is frustrated superradiant phase transitions, particularly in the presence of time universal symmetry breaking, provides this very natural model to explore this nice frontier of statistical physics. So I think experimentally assessing this type of a mechanism, I think it will be exciting directions. And now that was the n equal to
I think there is a question from the audience. Bernardo, you raise your hands.
Yeah, I cannot raise. I see the raise at the hand. Yes. So please speak.
Can I? Just a question. There is such a critical slowdown phenomenon, like in phase transition near a critical point in this case. You know critical slowdown?
Yes, yes.
The question is,
could you?
Could you repeat your question, maybe?
The question is, you are able to show, or there is a critical slowdown in this phase transition phenomenon that you show for one atom or for more than one atom? Near the critical point.
Yes, yes. So in fact, this closing energy gap is the critical slowing down, because the characteristic time scale of any dynamics will be determined by inverse of this smallest energy gap. So this closing energy gap will give you this critical slowing down. So the answer is yes. We see critical slowing down. Yeah, thank you. So then for N5, if you look at the phase diagram, this becomes actually more interesting. So in the presence of the synthetic magnetic field, so again, on the x-axis, I'm controlling the amount of flux, and on the y-axis is the light matter interactions. So then now you see a series of first order phase transitions. So within the frustrated Superradiant phase, there is one more first order phase transitions where you change the configurations. Here on the left hand side, we have up, down. So from the left, down, up, and one side creates the domain wall. So that will be the one kind of frustrated Superradiant phase. And if you see this green color in the middle, it has now a ferromagnetic domain. These three sides will have up and two sides down. So this domain wall type of frustration also occurs. So that it is distinguished from the blue one. So, and it is connected by the first order phase transitions. So as you crank up the critical flux, the synthetic magnetic flux, you have this series of first order phase transitions among different types of the Superradiant phase transition. And this can be understood very nicely by integrating out one of the quadratures of the cavity field. Each cavity field is complex number, so it can have a real part X and the imaginary part P. And you can integrate out this P part and create derive an effective mean field energy of the X. And this is what I showed here, EGN. It only includes the local position quadrature of the cavity field. And once you do that, you see on the right-hand side, there is this effective interactions whose range is not nearest neighborhood anymore. So we start with the nearest neighborhood interactions. That is our physical interactions. But if you integrate out the momentum quadrature, it effectively creates a long-range interactions among the X quadratures. And on the bottom, I drew effective J strengths. There is a nearest the neighborhood interaction M1, and the next neighborhood interactions M2, right? And you can see their relative size and the magnitude will change at this critical value of the synthetic flux. So basically, you can understand this in terms of a J1, J2, J1, J2 type of easing, antiferromagnetic easing interaction. You know, if you have a nearest neighborhood interactions or next neighborhood interactions, the kind of geometric frustration you can induce depends on their relative magnitude and relative size. And depending on that, you can have different types of configurations. And we could perfectly explain what is happening here in terms of these J1 and J2 interactions induced by superradiance. Okay. Well, then in this point, you have either one multi-critical point in the N3 case. You can have a multiple multi-critical points on the in the N5 case, and at this multi-critical point, you know, the excitation shows even a funkier behavior where you have two closing energy gap on both sides of the phase transitions with different exponents, right? I mean, this I think shows you some flavor that due to the frustrations and with the interplay with the time universal symmetry breaking, this anomalous critical scalings appears in several different ways. Okay, I mean, so now I think I'm going to wrap up this case. Well, then, what we have done so far is studying what is happening in the 1D and from the small size or the from to the larger size. But now you can naturally think about like what happens in the 2D lattices. And in the 2D lattices, you can have different choices. You can have triangular lattices or Kagome lattices. Then this competition between the sign frustrations and also ability to adjust the local amplitudes, so that could sometimes alleviate the frustrations, or sometimes it actually strengthens the degrees of frustration. So that is a very interesting competition happening in 2D, right? And so this is a work that we are preparing. I think we hope we are putting something out very soon, so you can stay tuned. So just to summarize, I hope I gave you some understanding of what we call the phenomena of frustrated superradiant phase transitions, right? So we just take a very old and important model in quantum optics, the decay model, and put them on the lattice and control the sign of the photon hopping. Just simply by doing that, you can induce geometric frustrations, and then the kind of physics you get out of is very rich. So I hope well, we have more investigation along this line. Okay, so I think I'm done.
Thank you a lot. So are there any questions?
One question. Perhaps I lost something, but I didn't understand well why at the critical point the fluctuation does not diverge. What is the physical reason?
Could you
So
ask the question one more time?
So sorry, Bernardo, you go.
Yes, you mentioned that there is no divergence of fluctuation at the critical point recently.
Right.
Yes. So the question is, normally there is divergence in the normal phase, second order phase transition. So why this happens? What is the physical reason? According
So
you have seen thing about it.
Yeah, so the physical reason is this asymmetric dispersion. So this epsilon k is the dispersions, so basically the energy of each momentum mode. And when we have a time universal symmetry breaking, then the frequency of the right moving photons and the left moving photons will have different frequencies. So that is the delta k. So it can pick up a negative sign. And when we are modulating theta, then at the critical point, this epsilon k just simply becomes negative at the critical point without having any square root singularity, meaning this ak remains positive while the energy gap closes. Well, then now look at what is this role of square root singularity in the photon number. It appears in the denominator of the photon number. So typically, the reason why we have a divergent photon number in the decay model is due to this square root singularity. You have its inverse will determine the divergence of the fluctuations. But because of this asymmetric dispersion, even without having this ak being 0, so it's square root singularity, you have a unstable normal mode. So that's the reason why we have this not diverging photon number at the critical point. So I would say the physical reason is this asymmetric dispersion.
Sorry, this mechanism forbid is like forbid the correlation at all scale to in such a way there is no divergence or fluctuation, right?
Yeah, at least in the normal mode, yes.
Okay.
Because any normal modes, however non-local that is, will have bounded fluctuations. So you cannot have a diverging correlations in this case.
Thank you.
Yeah.
Thank you.
Thank you.
So do we have other questions? If not, I think we already had some during the talk. So I would thank Myung-Joong for the very nice talk. And also thank you for your time.
Yeah, thank you for having me.
Yeah, it was our pleasure. So, okay.
Thank you.
Right.
Okay,
So
then.
hope to see you guys in person sometime
Yeah,
later.
yeah, sure. See you.
Sure.
See you.
Bye bye.
Bye bye.
Bye.
Thank you.